So good morning, welcome, happy Friday. Couple of things about today. So today at 1:10 p.m. in 2501, we'll take our first lab. This lab's going to be pretty chill. If you bring a copy of the chromatography lab, that would be super helpful. Also bring your calculator. You don't have either one of them, it's okay. I will spot you on this one, but try to bring those things and you'll be good to go. We'll start in 2501 at 1:10. Around 3 o'clock, we'll go to lab, do the chromatography lab. Should be pretty cool. Today, I will not have a 10 a.m. office hour. I apologize. We have a science division meeting. I had an 8 a.m. office hour, but I will be there at noon. So if you have questions on anything, you want to pop in at noon, no worries at all. And finally, Monday, Martin Luther King Jr. Day, Mount Hood Community College, totally closed. That includes the LSC, the Abbott Center. We won't have a lecture here, 9 a.m. I won't have office hours, stuff like that. But I monitor email all the time. You know, I'm addicted. So anyway, questions on any of that kind of stuff? We talked a lot in the last couple of days about Lewis structures, which are ways to talk about how electrons are distributed around atoms. And that's kind of like if you have a piece of toast and you want to put the jam like evenly distributed, or maybe you have more jam on the right side and less jam on the left side. That's kind of where Lewis structures come in really handy. But this next section we're going to talk about is also really handy. It basically is about how electron repulsion dictates geometry. So we've seen some examples in my pictures of molecules that are flat. Some have three-dimensional structure, and we're going to start looking into why they are. VSEPR is an acronym for valence shell electron pair repulsion theory. Now, valence electrons are the outermost atoms, the ones that are involved with bonding. And when those electrons in the outer parts start to get too close to each other, they start to repel. In chemistry, opposites attract, but like charges repel. So negatives get too close to each other, they start to back away. So VSEPR is going to be a big part of the stuff we're going to talk about here.
According to VSEPR theory, the valence pairs surrounding an atom move to positions that minimize their repulsions.
So these are like electrons around a central atom. The central atom would be the middle right there. And as there are more and more electrons added, the electrons try and get further and further apart from each other. Now, I'm going to show some videos, talk about some names and stuff like that. But man, I would love to have 2 volunteers join me that don't mind being in my video. Anyone? Clifford, thank you. Anybody? Thank you. Caleb, come on down. I appreciate it. All right, thank you. Thank you in advance for doing this. I'm the central atom. I'm the focus of the attention, I know. And Clifford and Kaylin are other bonds. So for example, maybe I'm carbon and they're oxygens. And notice how automatically, right across from each other, this is what VSEPR is all about. All right, they start getting too close to each other, then they start to feel a little weird and stuff. It's like, well, I don't know about the, Puss in Boots movie, whatever. Anyway, they're totally different. But their normal way is to be 180 degrees from each other. Can I have a third volunteer? Thank you, Aiden, for coming down. I'll put on my mask if you want, man. It's no problem. So I haven't been able to do this demo for a long time. Now, we may have to be over here a little bit. So move over here, gang. So yeah, thank you. So now I am once again the central atom, but look what happens, all right? They want to be as far apart from each other as they can, which is the normal way, all right? This is an example of a different orientation. Now before it was 180, all right? They were straight across from each other. Now, if you use your imagination a little bit, this is more of 120 degrees. In a circle, which is basically what I'm looking at around myself, all right? You 360 divided by 3 would be 120. So if the central atom has 3 pieces around it, like some of the boron compounds, trigonal planar is the most normal way. Now, I'm not going to bring a 4th person down, but what would be tempting to say is maybe that 4th person would be here to my right. We'd have then like 180 degrees from Aiden in the 4th person and 180 degrees here. But there's a little bit better orientation you can get with a tetrahedron. So when you get to 4 pieces, it's a little bit different than if you have straight across. If you had everybody straight across like in an X, the angles would be 90 degrees. But because this is a three-dimensional world, if I took Samuel and I put him above my head, like I go to the gym that much, but let's say I did, then you'd have actually 109 degrees. And the further apart these electrons can be, the better. All right, thank you all for being my models. I appreciate it. So yeah, totally cheesy. So all this VSEPR is, it's about electrons trying to get as far apart from each other as they can. All right? Now, when you have two, when it was just Kalen and Clifford, no problem. 180 degrees, far apart as they can. That's as happy as these things get. VEF2 is an example of a molecule that actually does it. The beryllium has no lone pairs on it. The fluorines are far apart from each other. And we refer to this as a linear geometry. Now, when Aiden came down, then we have a new dynamic, all right? You get the best bang for your buck, if you will, if all three of the atoms around the outside, around the central atom, are at 120 degrees. And this is what we call the trigonal planar geometry, all right? It's a flat molecule. You can see this thing as it rotates. It has just X and Y components, basically. Boron trifluoride, which we looked at a little bit the other day, is an example of this piece. Now, if you add a fourth piece, this is where chemistry is a little strange, and I think this is the main reason why organic chemistry is so frustrating sometimes to people. A fourth atom, it might be tempting to think that you'd have up and down, left and right, which would give you 90 degrees in a two-dimensional world. But in a three-dimensional world, you actually get better bond separation, i.e. the bond angles are further from each other if you place them in a tetrahedron. Now, a tetrahedron has four sides. That's where the tetra part comes in. And all the angles in a tetrahedron are about 109. 109.5, et cetera, 109 is totally fine. But a tetrahedron is better than having things straight across from each other. We go to a three-dimensional world, if you will, instead of just having two dimensions. So these things right here, linear, trigonal planar, and tetrahedral, are what they call electron pair geometry, and they're going to be really important. At this point, I would like to advertise a guide that's going to be your best friend for a while now, and it's called the Geometry and Polarity Guide. And I've tried to take lots of information from lots of different resources and place it in this, I think it's 4 or 5 pages and stuff. And in this Geometry and Polarity Guide, it has the names of these different electron pair geometries, as well as what's called a molecular geometry we'll talk about here pretty soon, bond angles, polarity, which is something else we'll talk about. So again, I highly recommend you check out this Geometry and Polarity Guide for next week. It'll have a lot of these names and stuff inside. Any questions on that? Okay, so the other day we talked about the Lewis structure for ammonia, and ammonia had a nitrogen with 3 hydrogens and a lone pair on the top. All right, so if we want to talk about ammonia in terms of VSEPR theory, we're going to be looking for 2 names. One of them is called the electron pair geometry, or EPG. The other one is called the molecular geometry, or MG. Now, the first one you can do right away is find the EPG, the electron pair geometry. Electron pair geometry allows you to see, if you will, the lone pair. And a lone pair is like having another bond. It takes up its own space. So nitrogen has what I'll call 4 clouds around it. 3 of the clouds are connected to hydrogens. 1 of the clouds is connected to a lone pair. But those 4 clouds, again, are really nothing more than negative lone pairs trying to get as far apart from each other as they can. So NH3 has tetrahedral electron pair geometry. If I asked you for the EPG of ammonia, you would say tetrahedral. The Geometry and Polarity Guide will have this in it as well. It'll say 4 clouds, 1 lone pair, 3 atoms. Cool. But there's another thing that's really handy. We talked in Chem 221 how electrons are kind of like shimmering, and they have these orbitals where they are most of the time, but you're never totally sure where they are. In chemistry, we want to know the energies, but we don't worry so much about the exact positions. So the other thing that's really helpful is to think about what this molecule would look like if the electrons were invisible. Now they're there, all right, they're having an impact. This is a big source of negative energy, but you wouldn't really see anything. So the molecular geometry is kind of what it's called when the electrons are there but invisible. And the name of this particular geometry is called the trigonal pyramid, or trig-pier. Trigonal pyramid is chemist's best interpretation. It's like a three-sided pyramid, all right? It's not a flat molecule because that lone pair needs its own space. So when it comes to a VSEPR description of ammonia, we would say that EPG, electron pair geometry, is tetrahedral, and the molecular geometry, or MG, trigonal pyramid. This geometry and polarity guide will have these names, and if you're new to these names, this is going to be pretty handy for you. So, any questions? Okay. Water, good old H2O. All right. When you draw out a Lewis structure for water, hydrogen will never be in the middle. Oxygen has to be in the inside. And when you distribute the electrons, the oxygen has 2 bonds to hydrogen and 2 lone pairs on it. So if you wish to describe water with VSEPR, you would look at the central atom, in this case oxygen, 1, 2, 3, 4 clouds of electrons around it. 2 of the clouds are lone pairs, and 2 of the clouds are connected to atoms. So because there are a total of 4 clouds around this is going to be another tetrahedral electron pair geometry. Anything with 4 clouds is a tetrahedral EPG. Now ammonia had only 1 lone pair and 3 atoms, but it had 4 clouds, tetrahedral. Water has 2 lone pairs and 2 clouds, but again, 4 clouds total, tetrahedral. A caltrop is something that one of my students said, wow, that's a tetrahedron, and he was right. So I had to put a little cheesy picture in there and stuff. A caltrop is a fancy way of saying something's tetrahedron. So. Anyway, back to the discussion. Molecular geometry is also important because these 2 lone pairs right here are kind of like invisible. So if you think about this structure right here, the HOH, it's not straight across. The Lewis structure looks like it's straight across, but the actual geometry, no, it's not straight across at all. We'll see in a little bit, it's about 109 degrees. So we would describe the molecular geometry of water as bent. Those 2 lone pairs in this picture, one's coming out of the screen and one's going into the screen, but they are there, all right? So water is not 180 degrees across. The Lewis structure absolutely looks like it's 180, but Lewis structures don't have any information on geometry. Chemists can't draw, all right? We're not artists, maybe photographers if we kind of use a liberal definition, but we're not artists, all right? And I can't draw anything. However, I can describe these things with a geometry then that will make sense. So you don't have to be Picasso or someone like that to be able to draw. So if I tell Clifford that, yeah, EPG is tetrahedral, MG is bent, he can then visualize in his mind what those 109 angles would look like and see. Any questions? Okay, so here's sulfur dichloride. All right, sulfur dichloride, when you draw out its Lewis structure, the sulfur's in the middle, chlorine's on the outside, 2 lone pairs on the sulfur. And the question is, which of the following corresponds to the molecular shape, which is molecular geometry, of SCl2? Well, first what we should do on a problem like this is figure out what the electron pair geometry is. And to do that, central atom, sulfur has 1, 2, 3, 4 clouds of electrons around it. What's the name of a central atom's geometry when there's 4 clouds around it? Tetrahedral. Well done. That's right. The electron pair geometry, the EPG of SCl2, would be tetrahedral. But in this problem, we want the molecular shape or molecular geometry description for sulfur dichloride. So S in the middle with 2 lone pairs, remembering that the lone pairs are invisible. It might be tempting to say, oh yeah, it's linear. No, that tetrahedral, those angles want to be 109 degrees from each other. It's not 180. So again, the drawings here are not accurate, all right? You have to think about in your mind, if you will, like what these different things mean. Anytime you have four clouds around it, the central atom is a tetrahedron, and tetrahedrons have 109-degree bond angles. So that's going to be a bent molecular geometry. This looks the same as water, all right? It's the sulfur in the middle of chlorines versus oxygen in the middle of hydrogens, but because there's four lone pairs, bent. Methanol is a type of an alcohol, and we're going to see as we go through this class that alcohols are actually a series of chemical compounds, all right? Now, drinking alcohol is by far the most common, probably. Just say no, kids. 19 in Canada, 21 here. Methanol is related to ethanol, which is drinking alcohol, but methanol makes you go blind, so don't drink methanol. Just say no. Anyway, neither here nor there. Let's draw the Lewis structure for methanol. Now, carbon's right here, 3 hydrogens and OH. Now, how many bonds can carbon have after our discussion the other day? What's the maximum number? 4. Now, here's where that comes from. Well done. Anything in the second period, lithium through neon, anything in the second period and higher is limited to 4 bonds around the central atom, all right? Things in the third period and lower can go more than 4, all right? We also talked about how boron, aluminum, beryllium can have less than 4, but carbon always wants to have 4. So when you have this molecule, carbon is going to have 4 bonds total. 3 of them will be connected to carbon, and the chemist is trying to give you a hint. There's an OH group off that 4th position. A lot of times when people are learning Lewis structures, they're trying to draw carbon with 5 bonds around it, like 4 hydrogens and an oxygen. But chemists are trying to help you out here and show that there's an OH group, which is actually pretty common in chemistry. So when you draw methanol out, this is the structure you get. Carbon has 4 bonds, 1, 2, 3, 4. Oxygen here, right next door, also has 4 bonds because oxygen is the second period as well. Oxygen has 2 lone pairs and 2 bonds. So methanol is a little bit more complicated of a structure. And why it's complicated is if Aiden looks at this and he says, well, you know, carbon here is going to have 4 bonds, but all bonds to atoms. Oxygen has 1, 2, 3, 4 clouds as well, 2 bonds to atoms and 2 lone pairs. So your geometry will be different depending on if you think the carbon is the central atom or the oxygen is the central atom. We'll talk about that. What we're going to do now is figure out the angles around atoms 1 and 2. And to do that, both carbon and oxygen have 4 clouds. They're both going to be tetrahedral systems. And tetrahedral systems are always 109. So that part is the same. But again, it's a little different environment here because this one has 4 bonds around it and this has only 2 bonds. For this atom, you would say it was tetrahedral electron pair geometry. And because all of the atoms are the same, you'd also have tetrahedral molecular geometry. But this one over here, with 1, 2, 3, 4 clouds, but 2 lone pairs, would be tetrahedral and bent. So I put up methanol here, not just because it's kind of a cute molecule to show rotating, but also because I want you to see that even though they're in different electronic environments, the angles are the same. However, the geometries will be a little bit different. Thanks for being patient with me.
So you put the 2 lone pairs on the oxygen because the hydrogen is only looking for 1 bond?
That's
the
right.
Oxygen wants 4?
That's right. Hydrogen will always be on the outside. Carbon and oxygen always need 4 pairs around them. You bet. And oxygen is going to have a 0 formal charge with 2 lone pairs if you want to figure out that kind of stuff too. Yeah.
So is that why we put the oxygen in the middle between C and H? And it's not because of the order it is in the molecule? So if it was something else and it wasn't involving hydrogen,
Right.
necessarily do that way, the reason is because H can only be connected to 1.
That's right.
Okay.
Sometimes, G, you'll see this listed as CH4O, and that's not as helpful because then it's a little harder to see that you have an actual OH group on it and stuff. But yeah, absolutely. This was chemists trying to help you out. Good. Good questions. Other questions?
What was MG of that called?
So the molecular geometry around the carbon would be tetrahedral. When all of the bonds are connected to atoms, the EPG and the MG are the same, Alex. But around the oxygen, it is different. This is like water. The oxygen is connected to 2 atoms with 2 lone pairs. It would have a tetrahedral / bent geometry. The tetrahedral would be the EPG, and the bent would be the molecular geometry.
So does that have 2 separate ones, or?
Yes, yeah. Alex is seeing it. When you get to more complicated structures, caffeine, whatever, alcohols, whatever, you can always use these rules, but they have to be relative to what you want to call the central atom, all right? So if you look at like vitamin C, for example, or any of these kind of things, yeah, you can always use central atoms for all the different things. It won't be for the full molecule, it'll be relative to what you're considering the central atom at the time. And we'll see this more in lab next week too. Cool. Other questions? All right, acetonitrile has a cyanide on the end of it. When you draw this molecule out, again, the chemists are trying to help you out a little bit here. A CH3 group we're going to see is called a methyl group. And this is CH3, this is the methyl group. It's very common in chemistry. CN, when you figure out its structure, it actually has a triple bond between it. So acetonitrile is CH3CN. And if I said, hey, what's the bond angles for angles 1 and 2? So angle 1 is this HCH angle. And to answer that, we need the electron pair geometry of that carbon. So if that carbon has 4 bonds around it, what's going to be its electron pair geometry? Tetrahedral. Well done. That's right. We use a lot of tetrahedrals in chemistry, so that's real common. Anytime you have tetrahedral, 109, all right? 109.5 is fine, whatever, but it's about 109. Now, a new player on the block, though, is this carbon. Now, this carbon has a single bond on the left and a triple bond on the right. And for reasons that we're going to look into in Chapter 8, the next chapter, I want you to think of double bonds and even triple bonds as just one big cloud, okay? So when you see a triple bond, it's not 3 individual bonds, it's just one big cloud. So around this carbon, 1 cloud here, 1 cloud here. What's the geometry when you have only 2 clouds? Linear. Well done. That's right. Linear geometries are always 180. So angle 1 here, not quite sure why I have a second one, but that's, I guess there's the angles. Oh. Cool, I didn't know. Anyway, all right, prop that back on. Anyway, angle 1, tetrahedral, 109. Anytime you see tetrahedral, 109 is a great answer. Angle 2, though, on the other hand, we're introducing here the idea that both doubles and triples are like one big cloud. And we're going to talk about this more in Chapter 8, so just hang on. But for right now, if you see a double bond or you see a triple bond, one big cloud. So this is a cloud, and this is a cloud. They want to be as far apart from each other. 180. Now, you can use all these VSEPR things to all the different molecules. And again, if this was Chem 104, Chem 151, we would never go beyond the tetrahedron. But in the big kids class here, we absolutely will go by. And you can use all these kind of rules when it comes to the things with 5 clouds around them and 6 clouds around them. And that's what we'll talk about right here. Now, when something is less than an less than an octet, all right, and that's usually boron, beryllium, aluminum, the rules are just the same. So here's BF3 again. The boron has 1, 2, 3 clouds around it. I've drawn it here like a 90-degree and 180 thing, but that's not the reality of this molecule. Those are all big electrons, and they want to get as far apart from each other as they can. So when I brought the three of you down earlier, you all kind of got into this kind of configuration. This is the trigonal planar or planar trigonal geometry, and that's what happens when you have 3 clouds around the central one. You can abbreviate this trig plane if you want, that's totally fine. Do not, though, call it just trig or planar, all right? You have to call it trig plane. There are other trigonal things and there are other planar things. So trig plane would be fine. I'm all about making things. I'm the lazy chemist if you've seen me talk to me before. But anyway, but there are other trigs and there are other planes. So now, when you have 5 or 6, it's the same kind of
According to
game.
VSEPR theory,
Trigonal
the
planar.
valence pairs surrounding an atom move to positions that minimize their repulsions.
Tetrahedral, 109.5. Now, this one now is called the trigonal bipyramid, and we're going to talk about what this thing is all about. And if you add a 6th one, you end up with what's called octahedral, all right? So 5 and 6 clouds, same idea. You want to keep them as far apart from each other. They try and get it far apart and stuff like that. I want to talk about this one right here. This is octahedral. Octa is 8, but there's 6 atoms around it, which I know is a little weird. If you're into geometry, the 3 points of the outside atoms is like one side. And there's 4 sides on the bottom and 4 sides on the top. So that's where the octahedral part comes from. I didn't make these rules, these are just what's saying it. So octahedrals have 6 pairs around them. That's a little bit weird, but no problem. Anyway, trigonal bipyramid is what happens when you have 5 atoms around a central atom, and there are lots of examples. Now remember, these will only happen 3rd period and lower. So this is phosphorus. Phosphorus number 15 is 3rd period and lower. Nitrogen right above it would never do this, all right? All those 2nd periods can go no higher than an octet, which means 4 pairs around it. But phosphorus and arsenic under that absolutely will do this. So PF5 is a trigonal bipyramid. There's interesting orientations around here. You have one set of fluorines that are literally 180 apart from each other. And then there's also like a trigonal planar in the middle, which is like a flat triangle. So in this combination, you have 90-degree angles, you have 120-degree angles, and even 180-degree angles. We're going to tackle this one more in the lab next week, so just realize it's kind of weird. Octahedral is basically when you have 6 atoms around a central atom, and this is very, very common. SF6 is a great example of this. Now, in this kind of orientation, all of your bond angles are either 90 degrees or 180 degrees, and that'll help you when we start figuring out different combinations. The game Jacks actually uses little octahedrons. I mean, they may not be perfect, but they're pretty close to it, so anyway. Real life applications. Again, Geometry and Polarity Guide will have these names and talk about the different angles and stuff like that. I highly recommend you check out the Geometry and Polarity Guide, which is in the companion and stuff like that too. Okay, so let's look at sulfur tetrafluoride, all right? Now, sulfur tetrafluoride, when you draw out its Lewis structure, there's a lone pair off the sulfur. So all the fluorines were happy, and there was one more lone pair right there. Now, sulfur is in period 3. Oxygen right above it would never make a molecule with more than 4 bonds, but sulfur and selenium and even tellurium below that absolutely will. So the question is, what's the geometry then? What's the VSEPR geometry around SF4? Well, when you have 1, 2, 3, 4, 5 pieces around the central atom, that's when you invoke the trigonal bipyramid. trigonal bipyramid is just a way that chemists talk to each other about a central atom having 5 pairs around it. So 4 of those are fluorines, and 1 of them is a lone pair around it. Now, technically, when you have 1 lone pair in this structure, you could make different isomers. But the nice thing about this particular molecule is that to keep the electrons as far apart from each other, the geometry is always going to put that lone pair in the middle trigonal planar part right there. It keeps the 90-degree angles, only 2 of them, and most of them are 120. So the punchline is that if you have 1 lone pair, you end up with what's called the seesaw geometry. Now again, chemists, need to get out of the lab more, but if you use your imagination, the SF4 part looks kind of like a seesaw, all right? There's a 180 and there's the 2 parts right here. And in grade school, like I was always one of the bigger kids, so it always went this way. And anyway, I don't have any problems. I've gotten through a lot of therapy. I'm fine now. But anyway, that lone pair is just invisible right there, all right? So the chemists think it looks kind of like a seesaw. That's where that name comes from. You don't have to see that. You don't even have to know what a seesaw is. But that's the official name then that chemists use to talk about a trigonal bipyramid with 1 lone pair. Any questions? Yeah.
So it had 34 total valence electrons, and I'm guessing the lone pair, is it supposed to have that sigma bond? Because let's see, 34 valence electrons, 17 pairs, minus
Cool.
5 sigma, 12. Okay, it's just, I don't know.
A sigma bond is when 2 atoms come together and their orbitals overlap, all right? But this is just a lone pair, Clifford, and that lone pair is just hanging out on the sulfur. So it doesn't have a sigma bond with it. Sigma and pi bonds are when you have atoms coming together, okay? This one's just hanging out on the sulfur itself, okay?
Why is it extended out the way it is? Like rather than just sitting directly on it like with the F?
Good question, too. 90-degree angles with lone pairs are really energetically unfavorable, all right? 90 degrees is a lot different than 109 or 120. And so in this molecule, these 2 fluorines try to get away a little bit from the lone pair right there. Gee, you brought up something really cool. A 90-degree lone pair with an atom is a lot higher energy than an angle that was 120 with a lone pair. And the more 90-degree angles you have, the more unstable the molecule is. So for example, you could put this lone pair right there and this fluorine right here. If the lone pair was up here, you'd have 1, 2, 3 90-degree angles with fluorine. And that just apparently upsets the molecule stability and stuff. So in this molecule, the F's, like right there, the equatorial ones are actually pushed out a little bit because this lone pair is like getting in their space. So
then if we have like homework where, we've added up to a certain amount of electrons and then we have extra ones that need to go on the central atom over the octet, would you prefer we illustrated that with a line, or can we just kind of put them off to the side, or what do you prefer?
cool. So because my drawing skills are horrible, this is all I would ask. All right. And this doesn't show any of this and stuff like that. These terms that are used to help chemists to visualize, I guess, what's going on. And if you have the drawing skills, boy, knock yourself out. That would be really cool. But man, my drawing skills, I can't even write my name very well. So that's why having just a Lewis structure like this is fantastic. And Lewis structures don't have to show any kind of geometry associated. Okay. Excellent questions. Now, these are the different names of the molecular geometries for the trigonal bipyramid and the octahedral system. So for trigonal bipyramid, if the central atom is connected by just atoms, the EPG and the MG are the same. So we would call the molecular geometry trigonal bipyramid for PF5. No lone pairs means EPG and MG are the same. Same for octahedral down here. Notice that in this version of SF6, all of the atoms around it are atoms. There's no lone pairs. EPG and MG are the same. But when you start adding 1, 2, or even 3 lone pairs, that's when the molecular geometry name starts to change. So we saw seesaw earlier for SF4. If you had 2 lone pairs, it would be called T-shape. 3 lone pairs actually makes for a linear molecular geometry. Octahedral with 1 lone pair, they call it square pyramidal, and 2 lone pairs, it's square planar. So this is why earlier I didn't want you to use trig or planar for the EPGs and MGs. There's a square planar and a trigonal planar. And likewise, there's a trigonal planar, a trigonal pyramid, and a trigonal bipyramid. The names start to overlap. So in this class, you've got to be very specific about what kind of EPG and MG you've got. These names are all in that geometry and polarity guide too. Yeah.
So it stops at linear. I'm just looking at the top.
Uh-huh.
Can it be reduced down to just 2 bonds and then, so there's, instead of being 3 atoms, there's only 2 atoms?
Yeah. You could have like HCl, something like that, but I don't know of any examples where you'd have 5 bonds around it. Like HCl would be chlorine with 3 lone pairs and a hydrogen. So it's not that you couldn't, I just honestly don't. So, cool. Yes, you can go beyond the octahedral, but we're not going to talk about those in this class. But you will see, especially if you do some research, molybdenum, tungsten, things like this, they make extra kinds of bonds, but more fun than you need on a Friday. So anyway, here's a molecule. It has 5 electron clouds, all right? And they might be pairs of electrons, they might be atoms, but it's around a central atom. The molecular geometry of this thing is linear, all right? Now, Aiden just noticed, which was really cool, that lone pairs, with so many lone pairs, you did end up with a linear molecular geometry. And the question is, how many lone pairs are present? Well, there's only, on a trigonal bipyramid, you've got up and down, and in the middle, you've got a trigonal planar, all right? If the molecular geometry is linear, that means the up and the down parts are actually atoms. So the middle parts are all gonna be lone pairs. If you think about this long enough, you're gonna have 3 lone pairs around the trigonal bipyramid. Trigonal bipyramids, again, have 5 possible spots, all right? If there's linear, then that means the above and below, those are actually atoms, but the other 3 in the middle, then, are going to be just lone pairs. So these are the kind of things you can start thinking about. Okay. Bond order is a super important thing when it comes to chemistry. Bond order helps the chemist to know how tough a bond is, how much energy it takes to break a bond, and you can also do some relative analysis as to how long and short bonds are. Now, this is an example of a molecule called acrylonitrile, all right? And notice how it has a double bond, a triple bond, and lots of single bonds. Bond order is literally the number of bonds between 2 atoms. So this carbon-carbon bond right here, bond order 1 bond. The double bond between these carbons right here means that this carbon-carbon bond order is 2 lines between them. And this CN here on the end, that would be a bond order of 3. The carbon-hydrogen bonds are all bond orders of 1. You don't have an overall bond order for the whole molecule, all right? You look at specific bonds to figure out what the bond order is. So when we talk about bond order, it's literally just the number of lines between those atoms, and this is why the Lewis structures are helpful and stuff like that. So, formaldehyde, good thing used in the funeral service area down below. It says, what's the carbon-oxygen bond order in formaldehyde? Now, this is what the molecule looks like from a molecular geometry. There's actually 2 lone pairs right there, but it doesn't really affect us. So to figure out what the carbon-oxygen bond is, you look for the number of lines between the carbon and oxygen. How many lines between the carbon and oxygen? 2, right on. So you'd say the bond order was 2 for the carbon-oxygen here. Okay. Now, most of the time, that's as simple as bond order is. You look at the bonds. If I said, what's the carbon-hydrogen bond order? You'd say it was a bond order of 1, all right? The only time it gets a little weird is when things resonate. And nitrite is a good example of that. NO2 minus, which we looked at, maybe, I don't know if we looked at it or not the other day. Anyway, nitrite, NO2 minus, is a molecule where you have a choice where the double bond goes. Initially, I wrote the double bond on the left side to the oxygen, but you could easily have the double bond be on the other side when it was on the right side. Now, if this molecule was frozen in space, you'd say there was a double bond here, bond order 2, and a single bond there, bond order 1. But in reality, that double bond is flipping back and forth, back and forth, back and forth. And if you looked at it over any appreciable amount of time, you wouldn't have a double and a single bond. You'd actually have about 1.5 bonds on each side. Less than a double bond, but certainly more than a single bond. This is what resonance is. You don't have one or the other. It's kind of a mixture of all of them. So to find the bond order for a resonating structure, you take the total number of electron pairs that are involved in the resonance. So in this molecule, there's 1, 2, 3 bonds, 3 lines between the N's and the O's. And you divide it by the number of places those bonds can go. And those bonds can go here or here, so 2 different places. So this bond order would be 3 pairs over the 2 places they can go. 3 over 2 is 1.5. All right. Now, why this is kind of cool to know about bond order is that bond order is inversely proportional to bond length, and bond order is proportional to bond energy. So what this means is that if you had a single bond versus a double bond, all right, bond order goes from 1 to 2. That means bond energy is going to go up as you go from 1 to 2. I've been babbling even since Chem 221. I'll shake Clifford's hand. Hey, good to see you. Single bond, someone breaks it up. Clifford, I haven't seen you forever. Double bond, it's harder to break up. That's what I mean here, all right? Bond order goes up, your bond energy goes up. I shake hands with Clifford with a single hand. Yeah, you can break it up. But a double hand, haven't seen you in so long, harder to break up. That's what this means. If you had a triple bond, it would be even harder to do. Now, the other thing I haven't told you as much, but I will say a little bit. A bond, single handshake. Clifford, good to see you. Clifford, I haven't seen you forever. I'm going to get a little closer to him. I'm so glad to see Clifford. What that means, bond order goes up, bond length goes down. And this happens with atoms as well. Bond order 2 is going to be shorter than bond order 1. All right? So that's why I've been doing all these crazy theatrics and stuff like that, trying to get things over. So if you know the bond order from a Lewis structure, which again is easy, 1, 1, 2, number of lines. Bond order goes up, bond energy goes up, which means it's harder to break those bonds. Bond order goes up, bond length goes down. They get shorter together. Now, these numbers here are a combination of X-ray diffraction and different computer studies. A picometer, all right, is a metric prefix. A pico is 10 to the minus 12, and we will use that once in a while at upcoming labs. And a kilojoule, just as a reminder, a kilojoule is 1,000 joules. Joule is the measure of energy that we use a lot of times in chemistry. So to break a carbon-hydrogen bond up, 414 kilojoules, bond order 1. But notice here, bond order 2, quite a bit more energy to break it up, almost twice as much. The bond orders depend on the types of atoms, blah, 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 so it's not quite that simple. However, in this case, you can see the bond energy is definitely higher. Now, what's not as easy to see is the bond length. I'll show you a better thing here in a little bit. You have to compare the right kinds of atoms together. By the way, an angstrom is another type of a unit that we'll see sometimes for bond lengths. An angstrom is not a metric prefix, but chemists use it a lot. I think they like little a with a circle on it, whatever. 10 to the minus 10 meters. We'll talk about that coming up here. All right, here are some better examples to show what I'm talking about here. Now, these values are in angstroms, and so this is 10 to the minus 10 meters, so really, really small. Why I like this example better, this is a carbon-oxygen single bond. This is methanol. Carbon-oxygen double bond, carbon dioxide. And this is a carbon-oxygen triple bond, carbon monoxide. So 1, 2, 3, bond orders going up. And these numbers are the bond lengths. So as bond order goes up, these numbers are going down. And this is why, Clifford, good to see you. Clifford, haven't seen you forever. Clifford! I'm not going to do it, man. Personal space, all the masks. COVID is not cool anymore. It probably never was. Anyway, prop that back on. This is what I'm talking about. Bond order goes up, bond length goes down. Now, breaking up those bonds is going to be higher energy, and I'll show you those in a little bit. But I wanted to show you a good example here of how if you're talking about the same types of atoms, carbons and oxygens only, then bond order goes up, bond length goes down. Now, here are some other examples. As you go left and down on the periodic table, the atoms get bigger, all right? So fluorine, chlorine, and iodine are all in the same period, and they're all connected here to the hydrogen. Fluorine is a lot smaller than chlorine. Chlorine is a lot smaller than iodine. Notice how the bond lengths here are getting larger. So that's why it really does depend what kinds of atoms you have, all right? All of these are single bonds, but the atoms connected to hydrogen are getting bigger and bigger and bigger, all right? So, hey, Clifford, what's going on? I've been at the gym. Oh, I haven't been at the gym as much. I'm a little bigger. Oh, hey, Clifford. And I haven't been eating way too much pizza, which is all I fantasize about some days. Long story short, prop that back on. I would be even fatter, and it'd be harder for me to grab onto Clifford and shake his hand, all right? Tell him an example, but that's kind of what it is. No disrespect to iodine, which is really important in the medical field. Punchline. Bond order goes up. Bond length goes down. On the other hand, bond order goes up, bond energy goes up. And it certainly depends on the types of atoms you have, all right? So this is a much bigger atom, bigger bond distance. This is a much smaller atom, smaller bond distance. All right.
Energy of a bond indicates its strength and is measured as the energy required to break the bond.
This is actually a table of bond energies we're going to use. These are all kilojoules per mole. They're all positive numbers. It takes energy to break up bonds. You're not going to have any negative numbers up there. It takes energy to break them up. What I'd like you to look at is the carbon-carbons. So carbon-carbon single bond, 348 kilojoules per mole. Double bond is more, 614. Triple bond, 839, all right? And for all of these, that's the pattern. Now, it's not quite like single times 2 is double, single times 3 is triple. It's not quite that easy, but that's a rough guess, all right? And again, as the bond order goes up, the bond energy, the energy required to break the bonds apart, certainly goes up as well. Here's some other examples of how this works out. Dioxygen, which is what we're breathing, has a bond order of 2 when you draw a Lewis structure. 498 kilojoules per mole to break it up, and the bond length 121 picometers. Now, hydrogen peroxide has an oxygen-oxygen single bond. And this is a double bond versus single bond order 2 versus bond order 1. So bond order has gone down, bond length has gone up, all right? Oxygen-oxygen single bonds are usually bigger than the double bond value. And as bond order goes down, the bond energy should go down as well. So it takes 498 kilojoules to break up O2 and 210 to break up O and O. Now, ozone, O3, has actually a resonating bond. It's a double single that can have 2 different waves. So the bond order for this would be less than 2, but more than 1. There are 3 lines and 2 places they can go. Bond order 1.5. Notice how the bond length is between the double and the single. So it's more than a single, but less than a double. And we would predict that the bond energy would also be between these 2 values, all right? Probably closer to 498, but that's not for sure. Definitely more than the 210 value. Now, how you can use these values is if you have Lewis structures, you can figure out the bond energies involved. The net energy of a reaction equals the bonds that you break minus the bonds that you form. So in that table I showed just a little bit ago, here are some values for HH, ClCl, and HCl. So this is a single bond, this is a single bond, and this is a single bond. Bonds broken minus bonds formed means bonds of reactants minus bonds of products.
Hydrogen and chlorine react to form hydrogen chloride. Because the total energy of the broken bonds is less than that of the bonds formed, the overall reaction is exothermic.
So for this reaction, the reactants are the bonds broken, and if you add up the HH and the ClCl, you get this number. The bonds that you formed are the product bonds. There are 2 HCl's, so 2 times 431 is 862. Bonds broken minus bonds formed would be 679 minus 862. This is a negative number, negative 183, and this shows that this reaction is exothermic. Energy is being released in this reaction. HCl is actually pretty easy to make. So you will need a table. You don't have to memorize any of the values of the table, that's for sure. Bonds broken minus bonds formed, bonds of reactants minus bonds products. Good to go. Okay, I'm out of time. I'll see you again at 1:10 p.m. or noon if you want to stop by for office hours. I don't have a 10 a.m. office hour. I have to run upstairs and go to a division meeting. See you.